The centroid of a planar region. Centroids of simple shapes. The centroid of a planar region is a point that plays the role of its center. One way to think of it is that if the region were a thin plate, one could balance the plate horizontally by supporting it at its centroid. If a region has a line of symmetry, then its centroid is on that line. If a region has two or more lines of symmetry, then the centroid is the point where they intersect. A simple disk has an obvious center that coincides with its centroid. Here's one line of symmetry, and here's another. Those lines intersect at the centroid. In fact, for a disk, every line through the centroid is a line of symmetry. Here's an equilateral triangle. A line through any vertex and the midpoint of its opposite side is a line of symmetry. So here there are three of them. The centroid of the triangle is the point where they intersect. For a rectangle, lines through opposite corners are lines of symmetry, as are lines through midpoints of opposite sides. For a regular pentagon, lines of symmetry are just as in the equilateral triangle. Each passes through a vertex and the midpoint of the opposite side. Other regular polygons have lines of symmetry similar to either the rectangle or the equilateral triangle, depending on whether there are an even or odd number of sides. We are more concerned, however, with less regular regions. A quarter disk, for instance, has only one line of symmetry. The centroid is somewhere on that line, but it's not obvious exactly where. Likewise for a half disk. A region between two curves, such as this, likely has no line of symmetry. Yet it will have a centroid, and we'd like to learn how to compute it. Moments. Let R be a region in the plane with area A. Think of R as a lamina, that is, a thin plate with uniform thickness. Assume that throughout this lamina the mass density is 1 unit of mass per unit area, then the mass of the lamina is numerically equal to the area A. That is, they're the same but with different units. Let x bar y bar denote the centroid of R. Then R's moment about the y-axis is defined as m sub y equals x bar, or the distance from the y-axis, times the area A. And its moment about the x-axis is m sub x equals the distance from the x-axis, or y bar, times the area A. Additivity of moments. Suppose that the planar region R consists of non-overlapping subregions R1 through Rn with areas A1 through An and centroids x bar 1, y bar 1 through x bar n, y bar n. Of course, the area of R is the sum of the areas of the individual subregions. Suppose also that x bar y bar is the centroid of the full region R, and that m sub y and m sub x are its moments about the coordinate axes, so that x bar times a equals m sub y and y bar times a equals m sub x. Now the moments m sub y and m sub x are the sums of the moments of the individual subregions R1 through Rn. That is, we can express our moments as m sub y equals the sum of x bar sub I times a sub I, and m sub x is the sum of y bar sub I times a sub I. So notice now that we have two ways of expressing each of these moments. M sub y is equal to x bar times the total area, and it's also equal to the sum of x bar sub I times a sub I. The moment about the x-axis is equal to y bar times a, and it's also equal to the sum of y bar sub I times a sub I. So we can now divide each of these by a to reveal x bar and y bar. X bar is the sum of x bar sub I times a sub I divided by a, and y bar is the sum of y bar sub I times a sub I divided by a. Now let's look at an example. Let's find the centroid of the region shown here. Now the irregular polygon here is actually composed of two rectangles. Now let's think about area. The circle there has radius 1, so the area of that disk is pi. The rectangle on the left is 4 by 2, so its area is 8. The other rectangle is 4 by 3, so its area is 12. So the total area is pi plus 8 plus 12, or pi plus 20. Now, to calculate our moments, we need to determine the centroids of each of the three parts of the region. To do this, we need a pair of coordinate axes. Notice we've chosen to put our origin at the bottom left corner of the rectangle with area 8. That's just a convenient choice. Where we place the origin is completely arbitrary here. The centroid of the circle now is clearly at the point 0, 6. The centroid of the left rectangle is at 1, 2. Notice that for the larger rectangle, the y-coordinate of the centroid is halfway between 2 and 5, or 3.5, or 7 halves, and so the centroid there is 4, 7 halves. Now that we have the individual areas and centroids, we can write down our moments. The moment about the y-axis is going to be the moment of the disk about the y-axis, which is the x-coordinate of the centroid times the area, and that's 0 times pi. Now let's go to the rectangle with area 8. The x-coordinate of the centroid is 1. The area is 8, so we have 1 times 8. Now for the other rectangle, we have x bar equal to 4 and an area of 12, so we have a 4 times 12 term. Now doing the arithmetic here, we have 0 plus 8 plus 48, or 56. Now let's get the moment about the x-axis. We take the y-coordinate of the centroid of the disk and multiply by pi, then the y-coordinate of the centroid of the area 8 disk times 8, and then add the y-coordinate of the area 12 rectangle times 12, and then calculate the sum. It ends up being 6 pi plus 58. Now we're ready to write down x bar and y bar. X bar is m sub y divided by a, which is 56 over pi plus 20, which turns out to be about 2.42. Y bar is m sub x divided by a, that's 6 pi plus 58 over pi plus 20, which is about 3.32. Now let's look at where our centroid lies in our region. Notice it's just about where we would expect it to be. Moments of a narrow strip. Suppose we have a strip that's parallel to the y-axis, like the one shown here, and suppose that its width is delta x and its area is delta a. Also assume that its horizontal midpoint is x, and the point at the top of the strip is x, y top, and the point at the bottom of the strip is x, y bottom. Now, because this is a simple rectangle, it's easy to determine where the centroid is. Of course, x bar is simply x, and y bar is the midpoint between y bottom and y top, or the average of those two numbers, 1/2 of y top plus y bottom. Also, the area delta A is equal to length times width, or y top minus y bottom times delta x. So, the moment about the y-axis is x bar times area, which is x times y top minus y bottom times delta x. And the moment about the x-axis is y bar times area, which is 1/2 of y top plus y bottom times the area y top minus y bottom times delta x. Notice that when we multiply those two middle factors out, we end up with 1/2 of y top squared minus y bottom squared, all times delta x. Now let's consider a region bounded by the graphs of two functions of x between x equals a and x equals b, with y equals f of x forming the top edge and y equals g of x forming the bottom edge. Consider a typical vertical strip centered at x with width delta x, noting that the centroid of the strip is located at x, 1/2 of f of x plus g of x. This thin strip has area delta A equals f of x minus g of x times delta x, and the full region has area A equal to the integral of f of x minus g of x times dx. The moment about the y-axis of a thin strip is x bar times the area of the strip, which equals x times f of x minus g of x times delta x. The moment of the full region about the y-axis can be approximated by summing the moments of thin strips, and in the limit as delta x approaches 0, those sums approach the integral from a to b of x times f of x minus g of x dx. The moment about the x-axis of the thin strip is y bar times the area of the strip, which equals 1/2 of f of x plus g of x times the area delta a. Delta a is f of x minus g of x times delta x, and when we multiply out f of x plus g of x times f of x minus g of x, we write this as 1/2 of f of x squared minus g of x squared times delta x. Now the moment of the full region about the x-axis can be approximated by summing the moments of thin strips, and in the limit as delta x approaches 0, those sums approach the integral from a to b of 1/2 f of x squared minus g of x squared dx. Next, we divide each of the moments by the area. X bar equals m sub y divided by a, and y bar equals m sub x divided by a. So to calculate the two coordinates of the centroid, we need to calculate three integrals, the area and the two moments, and then divide each of the moments by the area. Now let's look at an example. Find the centroid of the region bounded by the graphs of y equals x and y equals x to the fourth. Here's the picture of the two curves and the region bounded by them. Notice that it lives between x equals 0 and x equals 1. Now let's think about a vertical strip here, located at x. We'll first integrate the length of that strip over the interval to obtain the area. The integral from 0 to 1 of x minus x to the fourth dx is equal to 1/2 x squared minus 1/5 x to the fifth, evaluated between 0 and 1, which ends up being 1/2 minus 1/5 minus 0, and 1/2 minus 1/5 is equal to 3/10. Next, we'll calculate the moment about the y-axis. That's going to be the integral of the x-coordinate of our strip times the area of the strip, which is m sub y equals integral from 0 to 1 of x times x minus x to the fourth dx. Notice that's nearly the same as the area integral, except there's an extra factor of x. We'll multiply out the integrand to get x squared minus x to the fifth, and so now we integrate and get 1/3 x cubed minus 1/6 x to the sixth, evaluated between 0 and 1, which equals 1/3 minus 1/6 minus 0, or 1/6. Next, we calculate the moment about the x-axis. That's going to be the integral of the y-coordinate of the centroid of the strip times the area of the strip, which ends up being 1/2 the integral from 0 to 1 of the square of x minus the square of x to the fourth. So we have 1/2 the integral 0 to 1 of x squared minus x to the eighth dx, which equals 1/2 of 1/3 x cubed minus 1/9 x to the ninth, evaluated between 0 and 1, which is 1/2 of 1/3 minus 1/9 minus 0, which is 1/2 of 2/9, or 1/9. So now we're ready to calculate x bar and y bar. X bar is the moment about the y-axis divided by the area. That's 1/6 divided by 3/10, which equals 10 divided by 18, or 5/9. Y bar is the moment about the x-axis divided by the area. That's 1/9 divided by 3/10, which is 10 divided by 27. So the centroid of our region is the point 5/9, 10/27. Now let's look at another example. Find the centroid of the quarter disk in which x squared plus y squared is less than or equal to r squared, and x and y are both greater than or equal to 0. So our region here is the first quadrant portion of a disk with radius r. So let's notice that that quarter circle is the graph of y equals the square root of r squared minus x squared. Now there's a line of symmetry here, the line y equals x, and we know that the centroid must live on that line. So y bar will equal x bar. Also, we don't need to integrate to get the area of the region. That will be 1/4 of pi r squared. Now let's calculate the moment about the x-axis. That's going to be 1/2 of the integral from 0 to r of the square root of r squared minus x squared minus 0 squared, since the lower edge of the region is the line y equals 0. This simplifies to 1/2 the integral from 0 to r of r squared minus x squared dx. So we have 1/2 of r squared times x minus 1/3 of x cubed evaluated from 0 to r. The value at r is 1/2 of r cubed minus 1/3 r cubed. The value at 0 is 0. So we have 1/2 of 2/3 r cubed, which is 1/3 r cubed. So x bar and y bar are both equal to the moment about the y-axis divided by the area. That's going to be 1/3 of r cubed divided by 1/4 of pi r squared. So we end up with 4/3 of r divided by pi. Now that's about 0.424 times r, which tells us roughly where the centroid is along our line of symmetry. Now, although it's not necessary, let's calculate the moment about the y-axis to make sure that we get the same answer. The moment about the y-axis is the integral from 0 to r of x times the square root of r squared minus x squared dx. To do the anti-differentiation here, let's do a substitution. We'll let u equal r squared minus x squared, the quantity under the radical. Then du is minus 2x dx, so x dx is equal to minus 1/2 of du. Also, we'll transform the limits of integration. When x is equal to 0, u is equal to r squared, and when x is equal to r, u is equal to 0. So we have the integral from r squared to 0 of minus 1/2 the square root of u du. Now, since we're integrating from right to left and we have a negative sign, let's switch the limits of integration to get rid of that minus sign. Now, an antiderivative of 1/2 u to the 1/2 power is going to be 1/3 times u to the 3/2 power, and we evaluate from 0 to r squared, obtaining 1/3 r cubed. Notice that's the same as the moment about the x-axis, as it should be by symmetry. One more example. Find the centroid of the region in which y is greater than or equal to x squared and less than or equal to 1/8 times 7x squared plus 4. This inequality describes the region between two parabolas as shown here. Turns out the parabolas intersect at x equals plus and minus 2. Here the y-axis is a line of symmetry, and so by symmetry x bar will be 0. So we only need to calculate y bar. Now let's calculate the area. We'll take advantage of symmetry here and write the area as 2 times the integral from 0 to 2 of 1/8 7x squared plus 4 minus x squared dx. If we factor out 1/8, then the quantity in parentheses becomes 7x squared plus 4 minus 8x squared, and so we have 2 times 1/8, or 1/4, times the integral from 0 to 2 of 4 minus x squared dx. This equals 1/4 of 4x minus 1/3 x cubed evaluated from 0 to 2, which is 1/4 times 8 minus 8/3, which equals 8 over 4 times 2/3, or 4/3. Now let's calculate the moment about the x-axis. We'll take advantage of symmetry here to again integrate from 0 to 2. So our moment about the x-axis will be 2 times 1/2 of the integral 0 to 2 of the square of 1/8 of 7x squared plus 4 minus the square of x squared. Now we'll factor out a 1/8 squared here, which places a 64 in front of the second term, and then we'll multiply out 7x squared plus 4 quantity squared and simplify, and the result ends up being 1/64 times 49 minus 64 x to the 4th plus 56x squared plus 4 squared, or 16. We'll pull the 1 over 64 outside the integral and simplify, and so now we need to integrate 16 plus 56x squared minus 15x to the 4th from 0 to 2. Now we anti-differentiate. We have 1 over 64 times 16x plus 56 times 1/3 x cubed minus 15 times 1/5, or 3, times x to the 5th evaluated between 0 and 2. Now substituting 2 into that antiderivative gives us 1/64 times 32 plus 56 over 3 times 8, or 448 over 3, minus 3 times 32, or 96. 32 minus 96 is negative 64, which is negative 192 divided by 3. And so we get 1 over 64 times 448 minus 192 over 3, which is 256 over 192. The numerator there is 4 times 64. The denominator is 3 times 64. So we end up with 4/3 for the moment about the x-axis. So y bar is 4/3 divided by 4/3, or 1. So the centroid of our region is the point 0, 1. Notice here that the centroid is not in the region,